Welcome to the first lecture video for differential equations. In this section, we'll learn what a differential equation is, what the solution to a differential equation is, how to classify differential equations, verify solutions, and model mathematical situations with differential equations. Let's begin with an introduction to differential equations. First of all, note that algebra is used in solving simple, static problems, area, mixture, relations, etc. But problems involving changing or dynamic quantities, such as a growing population, motion, or temperature, can be represented by differential equations. Now, here are the goals of differential equations. Number one, we're going to model physical situations with differential equations. That is, we're going to translate a real-life situation into the language of math. Then, using our tools of mathematics, we're going to solve those differential equations. So, we translate, we solve, then we interpret the solution. That is, we translate from the world of math back to the real world to interpret the solution. So what exactly is a differential equation? A differential equation is any equation relating a function, its independent variable, and one or more of its derivatives. The key here is that the equation contains a derivative. They're very easy to spot because you'll recognize notation for a first or higher order derivative within the equation. For example, dy over dx equals 2xy is a first order differential equation that relates the function y of x, its derivative y prime of x, also known as dy over dx, and its independent variable x. Notice here that the Leibniz notation is very useful for distinguishing the dependent variable from the independent variable. Recall that in the expression dy over dx, the variable in the numerator is the dependent variable, and the variable in the denominator is the independent variable. We're very used to y being the dependent variable and x being the independent variable, but in the case of x becoming a dependent variable, again, Leibniz notation can be very useful. Let's look at example 1. Identify the function, derivatives, and independent variable for the second order differential equation given by 1 minus t times x double prime minus 4t x prime plus 5x equals cosine of t. So in this case, the function or the dependent variable happens to be x, or we could write it in function notation as x of t. The reason we know that x is dependent in this differential equation is because the derivative primes are applied to the x. Primes, or derivative notation, are never applied to independent variables. Since x in this case is dependent, we can assume then that t is the independent variable. The derivatives that we see in this differential equation are x double prime and x prime. Because the highest order derivative that we can find in this differential equation is the second derivative, we say that this is a second order differential equation. And we'll talk more about classification here in a minute. And finally, as we've already discussed, the independent variable for this differential equation is t. So the defining characteristic of a differential equation is simply that it contains a derivative. Part C, so what then is a solution to a differential equation? Well, to understand the solution to a differential equation, let's talk about something that we're very familiar with, that is algebraic equations. The solution to an algebraic equation is a number or set of numbers that balance the equation. For example, the solution set containing values 2 and 4 satisfies the quadratic equation x squared minus 6x plus 8 equals 0. So the solution to an algebraic equation is simply a number or a set of numbers. However, the solution to a differential equation happens to be a function. When we solve a differential equation, we're looking for a function whose derivatives balance the equation. For example, let's consider the differential equation y prime equals negative 2y. The general solution to this differential equation is y equals c times e to the negative 2x. Now notice at this point we're not actually solving the differential equation yet. We're just observing an example of a differential equation and its given general solution. From the differential equation, we can observe that the dependent variable is y, and we know that because the prime is applied to the y. Now, just looking at the differential equation, we don't know what the independent variable is. It could be x, it could be t, but from the general solution, that is y equals c e to the 2x, we can identify the independent variable as x. Now, c is a parameter or a real number that will be subject to a given initial condition. What we want to do is verify that this equation is in fact the solution to the given differential equation. Now, if we backtrack just a minute to our algebraic equation, the way that we would verify that these two values satisfy this equation is by using substitution, right? We would plug in both of those values independently and make sure that the equation is balanced. We're going to do the same thing with the differential equation. So notice our differential equation contains a first derivative y prime. So from our given general solution, that is y equals c e to the negative 2x, we can find the first derivative. That is y equals negative 2c e to the negative 2x. Here I'm just differentiating with respect to x, remembering that c represents a real number or a constant. Now, the given differential equation is y prime equals negative 2y. So where I see the y prime, whoops, forgot my prime over here, we're going to plug in this expression in the independent variable. And where we see the y in the differential equation, we're going to plug in this expression. Substituting these expressions in, on the left side we have y prime, which is negative 2c e to the negative 2x. And on the right side we have coefficient negative 2, and we're plugging in what we found for y, c e to the negative 2x. So this expression for y prime, which we obtained by finding the derivative of the solution, we plugged in for y prime. And this expression for y, we plugged in right here. And notice that gave us a balanced equation. So we can say, therefore, these three little dots mean therefore, y equals c e to the negative 2x is a general solution of the dE y prime equals negative 2y. So again, our differential equation contains a derivative, and the solution to that differential equation is a function. Now we're going to talk quite a bit more about this terminology of a general solution, but this is a general solution because it contains an arbitrary constant. C is an arbitrary constant, or parameter. We will examine how applying initial conditions allow us to specify a number for C for that arbitrary constant. For example, if we go from general solution now to particular solution, notice we have y equals 2 e to the negative 2x. Since we have a specific value in for that arbitrary constant C, we say that this is a particular solution. Now, in our general solution, because we do have that arbitrary constant C, we can see how this generates a family of solutions. we can see how changing the value of c will give us a different curve where each curve has essentially the same characteristics. Here's the specific particular solution we were considering, y equals 2e to the negative 2x, and I'm just judging these based on the y-intercept there. This one then would be y equals negative e to the negative 2x. This is y equals negative 2e to the negative 2x. And finally, y equals negative 3e to the negative 3x. There's actually an infinite number of solutions to this differential equation. Each of these individual particular solutions would also balance the original differential equation. So because there are an infinite number of solutions based on that arbitrary constant, we express the solution in this general form using that arbitrary constant. Now that you understand that a differential equation is an equation that contains a derivative and the solution to a differential equation is a function, let's talk about how we classify differential equations. There's two basic categories or types of differential equations. They are ordinary differential equations, which we often abbreviate as ODE or ODE, and partial differential equations or PDEs. In this class, our primary focus will be that first type, ordinary differential equations. Every once in a while, we'll pay attention to partial differential equations, but there's a whole different class devoted to solving partial differential equations. Not an easy class, by the way. We can express ordinary differential equations using a variety of notation. The first example that you see here, d squared y over dx squared minus dy over dx plus 6y equals 0, is called Leibniz notation. Remember, Newton and Leibniz discovered calculus at about the same time, but they used different notation. The benefit of Leibniz notation is that it's very easy to identify the dependent variable from the independent variable, and also the differential terms, the dy and the dx, they behave in algebraic ways. Another way to express that exact same differential equation is using what we call prime notation. Y double prime minus y prime plus 6y equals 0. Again, that's exactly the same differential equation. We're just denoting the derivatives a little bit differently. Prime notation is fast and efficient and very easy to write. Another type of notation that you'll be familiar with from Calculus 3 is subscript notation. With subscript notation, we can see both the dependent variable and the independent variable. Y is dependent, the subscripts there are the independent variables. So y sub xx represents the second derivative of y with respect to x, minus y sub x, that's the first derivative of y with respect to x. Now the last type of notation that we're going to consider is something that you'll probably see more in a physics class. It's called dot notation. The second derivative is denoted as y double dot. The first derivative then would be y dot. So again, these are four different ways of denoting the same differential equation. We call this Newton dot notation. This is primarily used for derivatives with respect to time. Now, when you see me write WRT, it means with respect to. So if I'm looking at a time derivative, maybe something like velocity or acceleration, and I use the dot notation, again, it represents derivatives with respect to time. Very useful in a physics application. Again, the second type of differential equation is a partial differential equation. An example of a partial differential equation is the second partial of u with respect to x squared plus the second partial of u with respect to y squared equals 0. We know that this is a partial derivative because we have the partial differential operator used in the notation. Notice on top, the variable u, that is the dependent variable or the name of the function, and we have two independent variables, x and y. Partial differential equations are used for multivariable functions. In the case of this partial differential equation, the solution would be some function u of independent variables x and y. And just for some variety here, we could also do this with the subscript notation, u sub xx plus u sub yy equals 0. So there's a variety of notation used with partial differential equations as well. But again, our focus is ordinary differential equations, and you will see them expressed using a variety of notations throughout the course. Another way to classify differential equations, in addition to type, is by the order of the differential equation. The order of a differential equation is determined by the order of the highest derivative of the dependent variable in the equation. It's important to recognize that we're talking about the order of the derivative, not an exponent. So be careful to distinguish the order of a derivative from an exponent of a dependent or independent variable. Now contrast that with an algebraic equation. The order or degree of an algebraic equation is the highest exponent that I can find on the independent variable in that equation. However, the order of a differential equation is the highest order derivative that I can find regardless of the exponents present in the equation. For example, determine the order of the following ordinary differential equations. Also identify the dependent and independent variables. So example A is written with Leibniz notation. D squared y over dx squared plus 5 times dy over dx cubed minus 4y equals e to the x. First of all, let's identify the dependent and independent variables. With Leibniz notation, recall that the dependent variable is identified by the variable in the numerator of the Leibniz notation. So in this case, the dependent variable is y. That means the independent variable identified there from the denominator of the Leibniz notation is x. Now, based on the definition that we've discussed, what do you think is the order of this differential equation? Did you say 3? If you said 3, notice that this is an exponent on the derivative. It is not an order of the derivative. That's simply the first derivative raised to the third power. When we identify the order of a differential equation, we're looking for the highest order derivative. So this is a second order differential equation. This happens to be a nonlinear differential equation because we do have the first derivative raised to an exponent, but again, be careful to distinguish the order of the derivative from an exponent either on the dependent or independent variable. Let's look at example B. We have x prime cubed plus x double prime equals cosine of t. What is the dependent variable in this equation? Did you recognize it as x? Or if we wanted to write it in function notation, we could call it x of t. How do we know that? Because the primes are applied to the dependent variable. That leaves the other variable for the independent variable, which is t. Okay, look carefully at this equation. What would you suppose is the order of this differential equation? Now, remember, it's not 3. This is an exponent. That's the first derivative raised to the third power. The highest derivative that we can find in this equation is the second derivative. So this is a second order differential equation. In particular, and we'll learn this as the course progresses, this is a second order, non-linear, non-homogeneous differential equation. Lots of big vocabulary words coming up in our very near future. Now, we've already briefly discussed verifying solutions by substitution, but this is such an important topic. This is how you can always check the solution to your differential equation. As we mentioned before, to verify the solution of an algebraic equation, we use substitution. We can apply the same principle to verifying the solution to a differential equation, keeping in mind that we may need to determine some derivatives in order to do so. So let's give this skill a try. Show that y equals x e to the x is a solution of y double prime minus 2y prime plus y equals 0. Before we get started, here's a little pop quiz. What is the dependent variable in this differential equation? Did you say y? If you did, you would be correct. What's the independent variable? Well, by looking at the differential equation, we can't tell because it only consists of y's, but if we take a sneak peek at the solution, we can see that the independent variable here is going to be x. Now, what's the order of this differential equation? If you identify the highest derivative here as the second derivative, we can see that this is a second order differential equation. Keep in mind, we are not actually solving this differential equation. The solution has been given to us. Our purpose is to verify this solution. We will learn how to solve this type of differential equation in future sections. So to show that this is a solution, we're going to need the first and second derivatives. So we're going to start from the given solution, y equals x e to the x, and we're going to need to generate the first two derivatives. So the first derivative can be obtained by the product rule. So we take the first function x times the derivative of the second, plus the derivative of the first function, which is x, times the second. Now it might be beneficial to go ahead and factor out that e to the x to make our substitution a little bit simpler. And this will also simplify our second derivative. Using the product rule, we have the first function times the derivative of the second plus the derivative of the first times the second. Again, if we factor out the e to the x, we'll have left behind 1 plus x plus 1, or we can simplify that to x plus 2. So we're going to take our first derivative, our second derivative, and the given function, and plug those into our differential equation, y double prime minus 2y prime plus y equals 0. I'm going to go ahead and write the word sub to show that something new is changing here. So we know that the second derivative in terms of the independent variable is e to the x times x plus 2. The next term we have here is minus 2 times y prime, and we're going to replace y prime with its expression in terms of x. That is e to the x times x plus 1. Next we have the term plus y. Y is our given solution, x e to the x, and we're checking for balance. So I'm going to put a little question mark there to say, is this a balanced differential equation? Now you've got a couple of choices here as far as how you want to verify this algebraically. You could certainly distribute the e to the x and the negative 2e to the x and combine like terms, or what I'm going to do is factor out e to the x from the three main terms that we have there. If we factor out e to the x from the first term, that leaves behind x plus 2. If we factor out e to the x from this second term and distribute that negative 2, we'll have negative 2x minus 2, and factoring the e to the x from the last term, we have plus e to the x. Again, I'm still checking for balance here, so I'm going to put my little question mark. Notice when we combine like terms inside parentheses, we end up with e to the x times 0 or 0 equals 0, which is clearly a balanced equation. So we can make our conclusion and say, therefore, y equals x e to the x is a solution to the given differential equation y double prime minus 2y prime plus y equals 0. Notice that when we plugged in our derivatives here on this second step, that everything was in terms of the independent variable. Okay, when you plug in your solution and its derivatives, you shouldn't have any dependent variables left over. Also, if for some reason I were to plug in the solution and not obtain the balance, 0 equals 0, like we did in this example, we would know that the proposed solution is in fact not a solution. Let's try another variety of problem. Example 4. Find all values of r such that y equals e to the rx satisfies y double prime equals 9y. So again, I'm going to run a little pop quiz here. Looking at the differential equation, y double prime equals 9y, can you identify the dependent variable? Of course you can. It's y. How do we know? Because the derivative is applied to the dependent variable. What's the independent variable? Well, we can't see that in the differential equation, but we can see from the solution that the independent variable is x. So the solution also has a parameter r. R represents a real number. It's a parameter like c. So our job is to figure out all of the real number values of r such that y equals e to the rx satisfies the given differential equation. So we're going to approach this in the same way we did example 3. That is, we're going to take our solution y equals e to the rx. We're going to need to find the first two derivatives, remembering that r is a constant. The first derivative is r e to the rx, and the second derivative then would be r squared e to the rx. Our differential equation, second order, this one would be linear and homogeneous. You'll learn all of that very shortly. We're going to substitute what we found for derivatives into this differential equation. So we're going to start with y double prime, which is r squared e to the rx, equals 9 times y, and y is e to the rx. Being careful not to divide both sides by something containing a variable, I'm going to collect all of the terms over here on the left. And then we can factor out the e to the rx term. That's going to leave behind r squared minus 9 equals 0. Then we have two factors multiplied equal to 0. So we know by the zero factor principle that we can set each of those factors equal to 0 individually. Now, the first factor, e to the rx equals 0, is actually an absurd statement. E to the rx is never equal to 0. Think about the graph of an exponential function, whether it's an increasing exponential function or a decreasing exponential function. There's a horizontal asymptote on the x-axis, so an exponential never equals 0. So I'm not going to get any information about r out of that first root. Out of this second equation, r squared minus 9 equals 0. You can solve that either by factoring the difference of two squares there or by using your square root property. We're going to come up with two distinct values of r, positive 3 or negative 3. We can say, therefore, y equals e to the rx is a solution to y double prime equals 9y for r equal to plus or minus 3. So that's a pretty straightforward example, but actually it's a pretty important example. You just did something called finding the roots of a characteristic equation. That's something that's going to be really important to us coming up very soon. Again, the purpose of this lesson is basically an introduction to differential equations, their solutions, verifying solutions, and finally here, the last concept we want to talk about, mathematical models and initial value problems. For those of you going on to be engineers or to study mathematics or physics, here's what's really important that you need to gain from your study of differential equations, and that is constructing a mathematical model. A mathematical model consists of a list of variables or unknowns that describe a real-world situation, together with one or more equations relating these variables. So we're going to take a real-world problem and we're going to translate it into the language of mathematics. Once inside the framework of mathematics, we will have tools that we can use to solve that problem. Then again, we can translate that solution back into the interpretation of the real-world problem. And this is where mathematics becomes very useful. We're also going to study something called initial value problems, which we'll abbreviate quite often as IVPs. Sometimes we'll look at boundary value problems or BVPs. So more information about that soon. Let's begin practicing writing our own models or writing a differential equation. Example 5, we want to write a differential equation to model the following situations. And we're going to start out really simple just to get used to this. So we'll go back and steal a Calc 1 style problem for our first example. The line tangent to the graph of g of x at ordered pair xy intersects the x-axis at x over 2, 0. So what we are attempting to do here is to model this tangent line using a differential equation. Now I'm going to draw a picture just to help us visualize what it is we're looking for. So we're going to have some sort of function. It's called g of x. I'll choose a random function here. This can model or be an example of g of x. And we're interested in the tangent line to this graph at ordered pair xy. Okay, xy is arbitrary. That means it can be any point on this graph. Okay, we're looking for the tangent line through this point that intersects the x-axis at x over 2, 0. That is, the x-coordinate of the x-intercept of the tangent line is exactly half of the x-coordinate where the tangent line meets the curve. So our goal is to write a differential equation to model this situation. Now, anytime we're working with tangent lines, we can express those using point-slope form. So let's think about starting with y minus y1 equals m times x minus x1, a familiar formula. X and y are general variables, so they will stay x and y, but x sub 1 and y sub 1 represent an anchor point on that line. So we're going to use the given ordered pair x over 2, 0 for x1, y1. Remember, anytime a variable has a subscript on it, it represents a constant. If the variable does not have a subscript like x and y, it's going to stay a variable. So using the ordered pair x over 2, 0, y1 is 0. We know the slope of this curve would be given by the first derivative y prime, and x1 here is x over 2. Now remember, we named our function g of x. So another way to write this would be g of x minus 0 equals g prime of x times x minus x over 2. So believe it or not, you just wrote a differential equation. You have an equation that contains a derivative. Now in general, we want to go ahead and isolate that derivative. So I'm going to simplify it just a little bit. Over here we have x minus x over 2. That's the same thing as x over 2. And solving for our derivative and flipping our equation around here, we would end up with g prime of x equals 2 g of x over x. Okay, and exploring a variety of notations here, we used y and y prime, we used g and g prime. We could also say something like the derivative of y with respect to x is 2y over x. Okay, so examine all of those different expressions. Here's the one containing y prime, of course, before I simplified it. Here's what it looks like using the function name g. Here's what it looks like using y and Leibniz notation. All of those differential equations express the same relationship. So this is a model of that tangent line on the graph. Perhaps the best expression is the simplest one. Looks like the Leibniz notation would be the winner here. So let's take a less geometrical approach on the next example. In a city with a fixed population of p persons, okay, we have a fixed population, so p then is what we call a parameter. That would be an actual number representing a given population. The time rate of change of the number n of these persons infected with the swine flu is proportional to the product of the number who have the disease and the number of those who do not. Now, I wrote this problem, or I lifted it out of our textbook before we had COVID-19. Do observe that a differential equation can be used to model the spread of COVID-19 in a population in a similar way that we're looking at the swine flu here. So let's glean the important information out of this problem. First of all, P is a number, a specific population. We could set that to be the population of Amarillo if that were the subject under study. Second, N is the number of infected persons. This is going to be changing as the swine flu spreads throughout the community. Now notice here we have the time rate of change. Rate of change indicates that we have a derivative. We're looking at the rate of change of the number of people that have the swine flu. If it's a time rate of change, we can express it as dn over dt. That is the time rate of change of infected persons. So how fast is the rate of infection spreading? Now, we're going to write our differential equation based on the way that the problem is expressed. It says the time rate of change of the number n of these persons infected with the swine flu is means equals, right? So the time rate of change of the infected population, dn over dt, is proportional to, okay, proportional to means we need a constant of proportionality. Generally, we call that k. Is proportional to the product, okay, so we're going to be multiplying, the product of the number who have the disease, remember the number who have the disease is given by n, times and the number of those who do not. Okay, now remember, we're dealing with a fixed population P. So if n people have the swine flu, we take the total population minus the number of infected people. P minus n would be the number who are not infected. So this is a very classic differential equation that can be used to model the spread of a virus through a community. It can also be used to model the spread of a rumor through a community based on this same differential equation. So notice here, n is the dependent variable. T, or time, is the independent variable. K is what we call a constant of proportionality. And P is a parameter, or the population. So K and P could both be classified as parameters. What's the difference between a parameter and a variable? A variable is a changing quantity that we're measuring, whereas the parameters, K and P, will be fixed numbers specific to a given community. Okay, so that rate of change may be different in a smaller community as a very busy city. So those again would be attached to a specific community. But once we had some statistics about that community, K and P would actually be numbers. So we call those parameters, not variables. The way that we find those parameters is often from initial conditions. So we're going to look at solving an initial value problem. Example B, or part B, use initial values to determine unknown parameters. Initial means what happens at the beginning of the experiment, or at time 0. So example 6, verify that y of x satisfies the given differential equation. So we're going to practice verification again. Then determine a value of the constant c so that y of x satisfies the given initial condition. So the first example here is e to the y times y prime equals 1. That's our first order nonlinear differential equation. The solution that's provided, remember we're not solving yet, is y of x equals natural log of x plus c. So the independent variable is x. C is a parameter. Now we have something new. Y of 0 equals 0. This is what we call an initial condition, which I'll often abbreviate IC. That's what we're going to use to determine a specific value of this parameter. In that case, we're going to progress from a general solution, that is one that contains an arbitrary constant, to a particular solution, or one that contains a specific value for C. So let's begin first practicing verification. We have the solution y equals natural log of x plus c. To show that this balances the differential equation, notice we're going to need a first derivative. The derivative of natural log of x plus c is 1 over x plus c. The given differential equation is e to the y times y prime equals 1. Now we want to substitute y and y prime into our given differential equation. So I'm going to replace y with natural log of x plus c, and I'm going to replace y prime with 1 over x plus c. We're going to find out, is this equal to 1? Now recall from rules of logarithms, you're going to see this a lot, so I'm going to write it formally here. If you have a base raised to a logarithm of that same base of some argument, this simplifies to give us an argument. That's an inverse property. You're actually plugging a logarithm into an exponential function because logarithms and exponents are inverse functions. They cancel out. In the case of the base e, it's going to look like e to the natural log of something. Again, that simplifies to give us just the argument of the log. So in the case of our problem here, we have base e raised to natural log, which is base e. That's going to simplify down to simply give us x plus c. Okay, the argument falls down. When we multiply that by 1 over x plus c, we do in fact verify that this is a balanced equation. So we know that y of x, we can say therefore y of x equals natural log of x plus c, solves the given dE, e to the y times y prime equals 1. So we have verified the solution. Now here's the new part. We want to apply the initial condition to go from general solution to particular solution, okay? So the general solution here is y equals natural log of x plus c. So our given initial condition is y of 0 equals 0. That is, we're going to plug 0 in for x right here, and we're going to plug 0 in for y right here. So when we apply this, we have 0 equals natural log of 0 plus c, or 0 equals natural log of c. And we can solve for c by rewriting it in exponential form, and we see that c is equal to 1. Running out of room here, so I'm going to borrow this space up here. We can say, therefore, the particular solution, that says particular if you can't read it, particular solution, we're going to go back and replace this c with what we found, natural log of x plus 1. So the particular solution then satisfies the given initial condition. Remember, the general solution yields a family of solutions. The particular solution is one member of that family. So this is pretty straightforward stuff. I don't think you'll have any problems with this first section. Enjoy this first section while it lasts. It's pretty simple. It's reminiscent of a lot of things that you already know based on your study of calculus. Let's try it again. We have y prime plus y tangent of x equals cosine of x. We have a first order differential equation, dependent variable y, independent variable x. We have a general solution provided, y of x equals x plus c times cosine of x, and we have an initial condition, y of pi equals 0. The first thing that we want to do is verify that the provided solution is in fact a solution or the general solution to this differential equation. So the given function, and I'm not going to write it in function notation, I'm just going to write it y equals x plus c cosine of x. To see if it balances our first order differential equation, we're at least going to need to find the first derivative, and this is going to require the product rule. So we have the first function x plus c times the derivative of the second. The derivative of cosine is negative sine, plus the derivative of the first function times the second. Now, the given differential equation is y prime plus y tangent of x equals cosine of x. And we're going to sub what we found into this differential equation. Remember, when you plug in your functions, everything should at that point be in terms of the independent variable. So looking at the first term in our differential equation, y prime, we're going to replace it with what we determined for y prime. Negative parentheses x plus c sine of x plus cosine of x. The second term is y times tangent of x. We're going to replace y with x plus c cosine of x, And remember, we had an extra tangent of x factor in the given differential equation. We want to find out, does this balance out to give us cosine of x? Now, if we look at this last term here, we have cosine times tangent. Recall that tangent is sine of x over cosine of x. So if we have cosine of x times sine over cosine, the cosines would cancel, yielding just a sine of x term. So we can simplify this as negative quantity x plus c sine of x plus cosine of x plus x plus c times sine of x. We want to know, is this equal to cosine of x? Now looking here at the very first and last terms on the left side, these two are opposite in sign, so they cancel. And we do, in fact, obtain a balanced equation. Cosine of x equals cosine of x. We can say our conclusion is therefore y of x equal to x plus c times cosine of x is the general solution to the given differential equation y prime plus y tangent of x equals cosine of x. Okay, good deal. Now we want to take the provided general solution. Remember, it's general because it has that arbitrary constant c, and we want to refine it to fit the given initial condition. The given initial condition is y of pi equals 0. Now remember, what's in parentheses here is the independent variable, so we're going to be plugging pi in for x, and out here is the dependent variable. We're going to plug in 0 for y. So we have pi plus c times cosine of pi, and our goal here is simply to solve for c. Okay, what is cosine of pi? I hope you said -1. I'm going to go ahead and divide both sides by -1 and solve for c to get negative pi. Now, we're going to loop this back around to our general solution, and we're going to refine it and make it a particular solution. That is, the solution that contains that given initial condition. So our particular solution then is y equals x. We're replacing c with negative pi, x minus pi, cosine of x. So the general solution balances the given first order differential equation. The particular solution would also balance that given first order differential equation, and in addition, it would contain the point pi 0. Technically, the condition that we're using here, y of pi equals 0, is a boundary condition, but it works just like an initial condition. An initial condition generally has an argument of 0. Let's consider one last model. Remember, our purpose here is to get to know what a differential equation is, what the solution to a differential equation is, verify a solution, apply initial condition, and begin studying models. So in example 7, we'll look at another model. Suppose that the time rate of change of a population P of t with constant birth and death rates is proportional to the population. Model this with a differential equation. So we're going to translate the problem from this English statement into the language of math. So let's go back word for word. We'll start with the time rate of change of a population. Notice here the function notation P of t indicates that P is the dependent variable, T is the independent variable representing time. So T is time, P is population. The time rate of change means we're talking about a first derivative. In Leibniz notation, this would be the derivative of P with respect to t. You could also denote that P prime of t. That would be equivalent. So the time rate of change of a population P of t with constant birth and death rates is translates into equals proportional to, when we see proportional to, we need a constant of proportionality to the population. Well, we were told that the population is P. So there we have modeled this situation with a very simple first order differential equation. Again, an equivalent way to do this with different notation, P prime of t equals Kp. Both of those are useful for different reasons, but they both represent the same situation. Now, keep in mind, we're not yet solving the differential equation. We're going to do that very soon. Example B says, show that P equals CE to the KT is a general solution that satisfies the differential equation. So again, I'm not showing you how to solve the DE yet. I'm saying if this is the solution, can you verify that this is the solution? So to show that this is the general solution, general because we have this parameter C, and also note we have the parameter K, which is our constant of proportionality specific to a given population. We want to show that this balances the differential equation, which means we need to find at least our first derivative. Now, focus here, the values C and K are numbers. The independent variable is t, so we are finding the derivative with respect to t. C is a constant, so it's going to filter through to the derivative. We're going to make a copy of the exponential exactly as it appears, and then we multiply by the derivative of the exponent. If k is a number, the derivative of that exponent is k. So a simpler way to write this, moving all of our constants to the left, is ck e to the kt. So it's important to distinguish what's a variable and what is a constant. It affects the way you handle your derivative. Now, the given differential equation is dp over dt equals kp. We're trying to verify that the given solution balances the dE. So on the left side, we have the expression dp over dt. We're going to replace it with what we found, ck e to the kt. We want to find out, is this equal to k times p? Well, we're going to replace p with ce to the kt. Now, multiplication is commutative, so we know that ck is equal to kc. So yes, we can say, therefore, we've established balance. P equals ce to the kt is a general solution of dp over dt equals kp. Now, we're dealing with a very basic differential equation here, but notice that this differential equation yields a solution that is exponential. Think about the things that are modeled by an exponential function. You could think about the growth of an investment in an account. You can think about population growth. You can think about the spread of a rumor through a population, or you could even go on the decay side of things, radioactive decay, or the decrease of medicine in your bloodstream over time. So the things that can be modeled by an exponential function then have a rate of change that can also be modeled by this differential equation. So this differential equation is actually very useful for many applications, and we'll study this pretty extensively. This is just sort of our first introduction. So C, further suppose that P of t represents the population of a colony of bacteria at time t. So instead of a population of people, we're looking at a population of bacteria at time t. So time is measured in hours. If there are initially, here are the initial condition, 1,000 units of bacteria, and the population doubled after an hour, what is the particular solution? Okay, we have a general solution. P equals ce to the kt. I'm going to rewrite that down here. Our general solution is P equals ce to the kt. Notice we have two parameters. We have c and we have k. In order to determine both parameters, we actually need two conditions. And within the context of this reading here, we do have two conditions. We have an initial condition. It says initially there are 1,000 units of bacteria. So at time 0, there are 1,000 units of bacteria. So I'm going to stop there. I'm going to apply this initial condition to find one of those parameters. Notice we're plugging 0 in for t, and we're plugging 1,000 in for p. So plugging this in, we have 1,000 equals ce to the k times 0. Well, e to the 0th is equal to 1, so we know 1,000 is equal to c. So our initial value is 1,000, And we can further refine our general solution now to be p equals 1,000 e to the kt. The coefficient of the exponential function is generally the initial value. Now, you may remember the Pert formula from college algebra, studying the growth of an investment in an account, where P was your original principal, right? Your initial investment. That's all we're seeing here, is that the initial value of the population, the investment, the radioactive element, whatever you happen to be modeling, generally lands in this spot right here. So watch for that pattern. Okay, so we still have an unknown parameter in our general solution. So let's look at the other condition here. We know by observation that the population doubled after an hour. So at 1 hour, we're going to plug in 1 for t, the population doubled. If our initial population was 1,000 and the population doubled after an hour, we know at this point the population is 2,000. So now we're going to use this additional condition to solve for k. So we're going to plug 1 in for t, we're going to plug 2,000 in for p from our previous solution. So we're going to get 2,000 equals 1,000 e to the k times 1. Let's divide both sides by 1,000. So we have 2 equals e to the k. Remember, our purpose here is to solve for k. So we can do this by taking the natural log of both sides, or if you just want to convert directly to natural log form, you can do that as well. Natural log of 2, natural log of e to the k is k. So we've found the value of our other parameter. Now, we are going to see this a lot, so I don't want to gloss over it just in case you're a little bit rusty on log rules. A moment ago, we said that e to the natural log of x is equal to x. If I reverse those two and I plug an exponential into a logarithm, then the exponent falls out, okay? And in a more general way, we could say log base b of b to the x equals x. So these are specific for e. Here is the more general rule. Please be familiar with all of the properties of logarithms, especially converting from log form to exponential form. We will do that quite often. Let me just show you that as well. If you have y equals b to the x, this is equivalent to log base b of y equals x. So those are equivalent expressions, okay? So I know you know that, but it's always good to review. Let's go ahead and finish our problem here. So we're going back to our last solution, and we're going to plug in what we now know for k. So the population p is equal to 1,000 e to the k, k is natural log of 2, times t. Now notice we have a multiplier for the entire natural log. That t is not multiplying the 2, the argument, it's multiplying the natural log. So I'm going to move it in front just to trigger your memory of another logarithmic property. Remember, if your logarithm has a coefficient, you can move that coefficient up into the exponent position. So this is 1,000 e to the natural log of 2 to the t. See all those levels? Again, let me be explicit here. If you have a logarithm of something raised to a power, that's the same thing as power times log of the argument. So you can move that power as a coefficient, or you can move a coefficient as a power. So that's the property that I used on that last step. Okay, now look at our exponential. We have e, base e, with a logarithmic exponent. So considering this property right here, we're going to get just the argument, right? Nope, not that property. This property, one higher. We have an exponential base. We have a logarithmic exponent. So according to this property, we simplify it by bringing the argument down. So this is 1,000 times 2 to the t. And you can see that exponential function expressed there. So just make some observations. The initial value of our population is now the coefficient of our exponential function. And the population doubled after an hour. You can see that reflected in the base of the exponential function. We have 1,000 times 2 to the t. So this is our particular solution. I want to remind you that we initially had two parameters. This is called a two-parameter family of solutions. We had C and K, and we had two conditions necessary to solve for those two unknown parameters. Okay, based on our solution, let's interpret our solution. What is the domain of this particular solution? Well, the function that we have here is P of t equals 1,000 times 2 to the t. This is a basic increasing exponential function. You can grab your calculator if you want to and take a look at the graph. Notice our independent variable is t for time and hours. Our dependent variable is p. Population, that's going to be measured as units of bacteria. Again, this is a basic increasing exponential function. We can tell that the y-intercept here, or the p-intercept, was our initial population. So at time 0, the population is 1,000. Now, what happens to this function over time? Because it is exponential, as t approaches infinity, the population of this bacteria also approaches infinity. So let's make the observation. The limit as t approaches infinity of our population function is infinity. Okay, that's really bad news. Remember, we were modeling a population of bacteria. So this is saying that over time, the population of that bacteria increases to infinity. So basically, the bacteria takes over the earth. That's not necessarily a feasible long-term solution. Well, let's say it this way. The domain of this function, the feasible domain, would be from 0 to infinity. Okay, now by saying this is the feasible domain, I'm omitting all of the negative possible values from the actual domain. Okay, so the actual domain of this function we know is negative infinity to infinity. But in the context of a model, and if t represents time, negative time doesn't make sense. So we're going to allow t to start at 0 and tick forward into infinity. But it's very likely that there are certain conditions that might affect the long-term growth of this bacteria. For example, the growth of this bacteria might be limited by conditions such as food supply, availability of sunlight, presence of predators, space available, disease, etc. So there's all sorts of external conditions that would interact with this model that would probably prevent that bacteria from taking over the earth. Therefore, we might say that a reasonable domain to consider would be something like 0 to a finite value. That is, this bacteria might begin growing exponentially over time, but then according to the presence of those conditions that we discussed, its growth is terminated or leveled out for some particular reason. So that happens a lot in models. You do have an interpretation of the solution, but it may not necessarily apply over the entire domain of your solution. So oftentimes we restrict the domain to model a particular time period for that aspect. Okay, great job. This completes your first section of notes, your first lecture video. Thank you for listening. I hope you learned something new and got to review some old things. You are now ready to begin your section 1.1 homework.